Chapter 8.1 Understanding Logarithms. Example, sketch the graph of y equals 2 to the power of x. We've sketched this several times in Chapter 7. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. Going in the negative direction, 2 to the power of negative 1 is 1/2. 2 to the power of negative 2 is 1/4. And 2 to the power of negative 3 is 1/8. Join those points together. And there's our graph of y equals 2 to the power of x. Part A, graph the inverse using your previous knowledge of inverses. So we should recall that for inverses, we can either reflect the graph across the y equals x line, or we can switch the x and y values of each point and plot those points as the points on the inverse. So I'm going to draw the y equals x line. And then I can either reflect the points across this line or switch the x and y values. So for example, if I start at the y-intercept, I have the point 0, 1. That would be the point 1, 0 on the inverse. Or I can reflect it across. So it is diagonally half a unit away from the y equals x line. If I go a half unit on the other side, I get to 1, 0. Then for the point 1, 2, flip the x and y values, we get 2, 1, which would be here. On the original function, we have the point 2, 4, switch x and y, that gives us 4, 2, which would be here. Then we have the point 3, 8, switch x and y, that gives us 8, 3. On the left side, we have the point negative 1, 1/2, which gives us the point 1/2, negative 1. Then we have the point negative 2, 1/4. Switch x and y, that gives us 1/4, negative 2. And negative 3, 1/8 was the last point we plotted. Switch the x and y, that gives us 1/8 and negative 3. Attach those points together. And that's the graph of our inverse function, which would be x equals 2 to the power of y. I'm going to write down the coordinates for some of these points. This was 8, 3. This was 4, 2, 2, 1, 1, 0, 1/2, negative 1, 1/4, negative 2, and last one, 1/8 and negative 3. Then if you're looking back and wondering how we got x equals 2 to the power of y, you'll be able to see that the points on that graph are the inverse of the points on y equals 2 to the power of x. And let's write a note here, graph the inverse. To graph the inverse, we switch the x and y values, or reflect across the y equals x line. Part B, what are the domain and range? Let's do the domain and range for both functions. So we'll make a table. We have the domain and the range. The first function is y equals 2 to the power of x. The second function is the inverse, x equals 2 to the power of y. The domain for y equals 2 to the power of x for this function here is xer, all real numbers. And the range for y equals 2 to the power of x is all y values greater than 0. Now let's look at the inverse function. We see that all the x values are greater than 0. So x such that x is greater than 0, xer. And for the range, we see that we continue down forever and also up forever. So the range is all real numbers. Part C, what are the x and y intercepts? Again, let's do this for both graphs. Y equals 2 to the power of x and the inverse, x equals 2 to the power of y. The x-intercept on y equals 2 to the power of x, we have no x-intercept because the range is y is greater than 0. So none. The y-intercept for y equals 2 to the power of x is when y equals 1, or the point 0, 1. Looking at the inverse function, the x-intercept, we have an x-intercept this time. It is when x equals 1, so the point 1, 0. And we do not have a y-intercept because the domain is x is greater than 0. So none for the y-intercept. What we should notice is that our domain and range switched. So domain for y equals 2 to the power of x is xer. The range for the inverse function is yer. The range for y equals 2 to the power of x is y greater than 0. And the domain for the inverse function is x greater than 0. Same with the intercepts. We have no x-intercept for the original function. And in the inverse function, we have no y-intercept. So those switch. And the y-intercept for the original function, y equals 2 to the power of x, is 0, 1. Then in the inverse function, the x-intercept is 1, 0. Part D, what are the equations of any asymptotes? Looking at y equals 2 to the power of x, we know that y is greater than 0. We have a horizontal asymptote at y equals 0. Then for the inverse function, we know that the domain is x is greater than 0, so we have a vertical asymptote at x equals 0. X equals 2 to the power of y has a vertical asymptote at x equals 0. Part E, what is the equation of the inverse? We have the equation of the inverse is x equals 2 to the power of y. Part F, how would we put this equation into our calculator to check our graph? So how do you solve for y? This is where logs come in. We need to use logs. The inverse of an exponential function is called a logarithmic function. The inverse of y equals 2 to the power of x is log base 2 of x equals y. The reason we use logs is to solve for a variable in the exponent. So to take an equation from exponential form, which is this, x equals 2 to the power of y, to logarithmic form, the base of the exponential function becomes the base of the log, and is written here, this subscript number. The argument, x, in the exponential function is written with the log, so this is said log base 2 of x. And then it equals the exponent. So our exponent was y. The log base 2 of x equals that exponent. Again, the number that is neither the base nor the exponent is called the argument. So this is the argument here. This is the argument in log form. Note, if you see a log written without a base, so this number here is not written, we assume the base is 10, which is known as the common logarithm. So just like with a root without an index number implies square root, a log without a base number implies base 10. So common logarithm is log base 10. So log x, there's no subscript here. Means base 10. To change from exponential form to logarithmic form, take your base and apply it as the small lowered number after the log. The answer of a log, or what it equals to, is always an exponent. Then fill in the missing number as the argument. Example, change the following from exponential form to logarithmic form. So in exponential form, we have a base of 5. The exponent is 3. And the argument is 125. We're going to write log and then the base, which is 5. Log base 5 of the exponent, which is 3, equals the argument 125. Now it's in log form. Next one, we have x equals 3 to the power of y. Our base is 3. Our exponent is y, which leaves x to be the argument. Then in log form, we write log base 3 of the exponent y equals the argument x. Next one, 4 to the power of negative 2 equals 1 over 16. Our base is 4. The exponent is negative 2. And the argument is 1 over 16. In log form, this becomes log base 4 of the exponent, negative 2, equals the argument, 1 over 16. So again, in log form, the base goes here. The exponent goes here. And this is the argument. To change from logarithmic form to exponential form, raise your base to the power of the number that stands alone on the other side of the equal sign, which is the exponent. This equals the number left over, which is the argument. Example, change the following from logarithmic form to exponential form. We have log base 10 of 100 equals 2. The number that's alone is the exponent. The number that's left over is the argument. In exponential form, this becomes the base 10 to the power of the exponent 2 equals the argument 100. Log base 6 of 1 over 36 equals negative 2. That's our exponent. And 1 over 36 is our argument. Then in exponential form, we write the base 6 to the power of the exponent negative 2 equals the argument 1 over 36. And last one, log base 2 of square root of 32 equals 5 over 2, which is the exponent, leaving root 32 for the argument. In exponential form, this becomes the base 2 to the power of the exponent 5 over 2 equals the argument, square root of 32. Note, log base b of b to the power of n equals n. For example, log base 3 of 3 to the power of 2 equals 2. So when we have the argument written as a power of the base, the answer to the log is the exponent on the argument. Using the log base b of b to the power of n equals n rule, we look at the argument to see if it can be written as an exponent with the same base. If it can, then the exponent of the argument becomes the answer. So log base 10 of 100 equals 2. Let's see why. We can write log base 10 of 100 as log base 10 of 10 to the power of 2, which by the log base b of b to the power of n rule, since the argument is written as a power of the base, the exponent on the argument, which is 2, is the value of that log. Log base 6 of 1 over 36, we can write that as log base 6 of 1 over 6 squared. Then we move that up, and we get log base 6 of 6 to the power of negative 2. And by the log base b of b to the power of n rule, the solution to this log is the exponent on the argument, since it's written as the same base as the log. So the answer to this is negative 2. Last one, log base 2 of square root of 32 equals 5 over 2. We can rewrite this log as log base 2 of the square root of 2 to the power of 5, which is 32. Then we can rewrite this as log base 2 of 2 to the power of 5 over 2. Remember, a square root is equivalent to 1 over 2 as an exponent. And then by the log base b of b to the power of n rule, this log is equal to this exponent 5 over 2. Evaluating logs without a calculator. Change logs into exponential form and solve from there, or use the log base b of b to the power of n equals n rule to solve if possible. Use the method you are more comfortable with. Example, evaluate the following. We have log base 3 of 27. We want to evaluate that. Let's start by using the log base b of b to the power of n equals n rule. So I can write this as log base 3 of 3 to the power of 3. 27 is 3 to the power of 3. By the rule, this log equals the exponent on the argument, so that equals 3. Log base 7 of 1 over 49. Write 1 over 49 as a power of 7. We get log base 7 of 1 over 7 squared. We move this to the top and we get log base 7 of 7 to the power of negative 2. By the log base b of b to the power of n equals n rule, this equals negative 2. Then log base 2 of 2 to the power of 7, that's already in log base b of b to the power of n form, so it's going to equal the exponent on the argument, which is 7. Now let's solve the other way. So, or write in exponential form and solve like we did in chapter 7. Log base 3 of 27 becomes 3 to the power of the exponent. That's what we're solving for. We could call it any variable. So x equals 27, the argument. Write 27 as a power of 3. 3 to the power of x equals 3 to the power of 3. Then we know from chapter 7 that the exponents are equal, so x equals 3. Next one, we have log base 7 of 1 over 49. Changing this to exponential form, we take the base 7 to the power of the exponent, which we don't know in this case, so x equals the argument 1 over 49. We want to write the argument 1 over 49 as a power of 7. We saw above that it equals 7 to the power of negative 2. Then we have that x equals negative 2. And then log base 2 of 2 to the power of 7. Write this in exponential form. We have the base 2 to the power of the exponent, which we don't know, so we'll call that x, equals the argument 2 to the power of 7. Then x equals 7. Next, log of 0.01. Notice there's no base, so that means log base 10 of 0.01. Let's write 0.01 as a power of 10. First of all, it's log base 10 of 1 divided by 100. Then this can be written as log base 10 of 1 over 10 squared. Move that to the top, and it becomes log base 10 of 10 to the power of negative 2. And by the log base b of b to the power of n rule, this equals negative 2. Log base 9 of the 5th root of 81 is log base 9 of the 5th root of 81 is 9 squared. Then we can write this as log base 9 of 9 to the power of 2 over 5. And by the log base b of b to the power of n rule, we get that this equals 2 over 5. And log base 16 of x equals negative 1 over 4. This time we're solving for the argument. If we use the log base b of b to the power of n equals n rule, this means that the argument x has to equal the base 16 to the power of the exponent negative 1 over 4. And we could simplify this. 16 can be written as 2 to the power of 4, and then to the power of negative 1 over 4. Then we multiply those exponents together. 4 times negative 1 over 4 gives us 2 to the power of negative 1, which then gives us 1 over 2. Notice that for this one, using the log base b of b to the power of n equals n rule is the same as writing it in exponential form since we're solving for the argument. So I wrote it in exponential form. I took the argument x equals to the base 16 to the power of the exponent negative 1 over 4. Let's go back to the first two and solve them by writing them in exponential form. So we start with log base 10 of 0.01. Write this in exponential form. The base 10 to the power of the exponent, which we don't know, x, equals the argument 0.01. Write both sides as base 10, so 10 to the power of x equals, we saw above that 0.01 is 10 to the power of negative 2. Then we get x equals negative 2. Log base 9 of the fifth root of 81. The base 9 to the power of x equals the fifth root of 81. Write both sides as base 9. 9 to the power of x equals 9 to the power of 2 over 5. Then x equals 2 over 5. Log base x of 9 equals 2 over 3. So this time we're solving for the base. Let's write this in exponential form. The base x to the power of the exponent 2 over 3 equals the argument 9. In this case, let's make the exponent on x 1. So what would we have to multiply 2 over 3 by so that we get 1? It would be the reciprocal. So x to the power of 2 over 3 to the power of 3 over 2. And what we do the one side we have to do to the other. So 9 to the power of 3 over 2. Then 2 over 3 times 3 over 2 is 6 over 6, which equals 1. So we get x equals 9 to the power of 3 over 2. We can calculate that. X equals the square root of 9 to the power of 3. Square root of 9 is 3, so x equals 3 to the power of 3, which is 27. Last one, log base 4 of x equals negative 2. So here we're looking for the argument again. Change it to exponential form. The base 4 to the power of the exponent negative 2 equals the argument x. And then we can simplify the left side. 4 to the negative 2 is 1 over 4 to the power of 2, which is 1 over 16. So x equals 1 over 16. The Richter magnitude m of an earthquake is defined as m equals log of a over a0, where a is the amplitude of the ground motion, usually in microns, measured by a sensitive seismometer, and a0 is the amplitude corrected for the distance to the actual earthquake that would be expected for a standard earthquake. Part A. In 1946, an earthquake struck Vancouver Island off the coast of British Columbia. It had an amplitude that was 10 to the power of 7.3 times A0. What was the earthquake's magnitude on the Richter scale? So the amplitude, A, was 10 to the power of 7.3 times A0. Using the formula for magnitude, we have m equals log of, notice we don't have a base, so that means log base 10. So log of the amplitude A, which we just said was 10 to the power of 7.3 times A0 divided by A0. We can simplify this. We have A0 on top and bottom. We don't know the value of A0, but we know it's the same, so we can divide those out. Then we have m equals log of 10 to the power of 7.3. Remember, this is log base 10, so we have log base 10 of 10 to the power of 7.3, which is the log base b of b to the power of n rule. So that tells us that m, the magnitude, equals 7.3. This is a word problem, so we should write a sentence. The magnitude of the earthquake was 7.3. B. The strongest recorded earthquake in Canada struck Haida Gwaii off the coast of British Columbia in 1949. It had a Richter reading of 8.1. How many times as great as A0 was its amplitude? So if it has a Richter reading of 8.1, that's saying that m equals 8.1. Again, using the formula for the magnitude, m equals log of a over a0, we get 8.1 m equals log of a over a0. Again, this is log base 10, and we can write this in exponential form. So the base 10 to the power of the exponent, 8.1, equals the argument a over a0. We want a, so we can isolate a by multiplying both sides by a0. And we get that a equals 10 to the power of 8.1 times a0. So we can say the amplitude of the earthquake was 10 to the power of 8.1 times a0. Part C, compare the seismic shaking of the 1949 Haida Gwaii earthquake with that of the earthquake that struck Vancouver Island in 1946. So when comparing earthquakes, we want to put the amplitude of one earthquake on top of the other. So we want to compare the Haida Gwaii earthquake to the Vancouver Island earthquake. So the amplitude of Haida Gwaii earthquake over the amplitude of the Vancouver Island earthquake, which equals the amplitude of the Haida earthquake we saw here is 10 to the power of 8.1 times A0. And the amplitude of the Vancouver earthquake we saw up here is 10 to the power of 7.3 times A0. Let's calculate this. We can divide out A0 because it's on top and bottom. And we get 10 to the power of 8.1 over 10 to the power of 7.3. Then using exponent laws, we have the same base, so we can subtract these exponents, 10 to the power of 8.1 minus 7.3, which gives us 10 to the power of 0.8. And then we can write a sentence. The amplitude of the Haida earthquake was 10 to the power of 0.8, or we can calculate that. 10 to the power of 0.8, about 6.3. So, or approximately 6.3 times as great as the amplitude of the Vancouver Island earthquake. Example, the largest measured earthquake struck Chile in 1960, measuring 9.5 on the Richter scale. How many times as great was the seismic shaking of the Chilean earthquake than the 1949 Haida earthquake, which measured 8.1 on the Richter scale? So we want to do the same thing as the last question. This time we're comparing the Chilean earthquake to the Haida earthquake. The amplitude of the Chilean earthquake measured 9.5 on the Richter scale. So using our formula, we have 9.5 equals log base 10 of A over A0. Write this in exponential form. We get 10 to the power of 9.5 equals A over A0. And isolate A by multiplying both sides by A0. So we get the amplitude of the Chilean earthquake is 10 to the power of 9.5 times A0. That goes on top of our fraction, 10 to the power of 9.5 times A0. And on the bottom is the amplitude of the Haida earthquake, which we had up here. 10 to the power of 8.1 times A0. And then we solve. Again, we can cancel out or divide out the A0s. we get 10 to the power of 9.5 divided by 10 to the power of 8.1. Using exponent laws, this is 10 to the power of 9.5 minus 8.1, which is 10 to the power of 1.4. And we can calculate that. 10 to the power of 1.4 is 25.1188, so approximately 25.1, we'll say. So our sentence, the amplitude of the Chilean earthquake was 10 to the power of 1.4, or approximately 25.1 times as great as the amplitude of the Haida earthquake. That brings us to the end of Chapter 8, Lesson 1.